All right, welcome to 52 Weeks of AWS, and I'm continuing on the AWS Security Certification. Today, I'm going to cover protecting data in your application. So let's go ahead and get started here. And I've got protecting data in your application as the first topic for today. And we can talk a little bit about, what this means in practice and walk through some of the initial things to cover. So at the end of the module, you're going to know about protecting data at rest and in transit, about Amazon S3 protection, how to encrypt data in Amazon S3, how to differentiate between client-side encryption and server-side encryption, and then also how to identify Amazon Web Services that help you protect your data. So really, this is the overview of what we're going to cover. So what I'm going to do here is I'm going to get down to a shared responsibility model. This is always a good place to start when you're thinking about, how to reason about a particular topic in security. So a shared responsibility model would list a customer and AWS responsibility. The customer is going to be responsible for the security inside of the cloud, and this would include customer data, the platform application, identity and access management, the operating system, the network, the firewall configuration, client-side data encryption and data integrity authentication, server-side encryption of file system and data, network traffic protection that includes encryption, integrity, and identity. And then in terms of AWS, it's responsible for the security of the cloud. So this includes things like the foundational services, so compute, storage, databases, and networking. And this module is going to cover the shared responsibility model, client-side encryption, and data integrity. And in particular, it'll cover the file system and the data. So let's go ahead and talk about how to protect the data at rest, which is a critical step in reasoning about data. If we think about what are the main concerns here, it's important to encrypt the data when it's at rest so that it's secure. So the security of the data is really guaranteed, because even if an unauthorized party gains access to it, the encryption of the data makes it much, much more difficult for an attacker to compromise the data, because even if they have access to it, let's say at the endpoint level, like an unsecured bucket, for example, you still have a layer of protection because you've added this encryption. So this would also enforce business and compliance requirements. So some of the things to consider would be in information disclosure, limit the number of users who can access the data, and also use policies to manage access to resources, and then use encryption to protect that confidential data. Also, data integrity compromise. So use resource permission to limit the scope of users who can modify the data, and also implement digital signature and encryption, and then have the ability to restore that data from a backup, or in the case of S3, even better, you can have object versioning, which allows you to go at multiple iterations at the object level, which gives you a granular control of backups. Also, accidental or malicious deletion. So in the case of a correct permission and principle of least privilege here, you're able to really limit the scope of the damage because of your ability to limit who has the ability to mutate things. And then in terms of system hardware and software availability, this would be like a system failure or natural disaster. So these are all things to consider when you're thinking about how to protect data at rest. So in terms of S3, which is really the big one to consider initially, is that buckets, objects, and also related sub-resources like lifecycle configuration and websites are private. So you don't really need to do anything unless you've explicitly turned on some extra permission. The only resource owner, the AWS account that created it, can have access to the account, and the resource owner can grant access permission to others by creating an access policy, and you can modify the bucket policies to allow additional access. And AWS also provides a number of tools to configure a bucket for a wide variety of workloads. So in the example of S3, you could actually block public access as a additional layer of protection to prevent an accidental, misconfiguration of data. And also you can encrypt the data at rest as well with S3. In terms of granting permissions, this is another thing to consider, which is, can you actually support both the identity-based permission and the resource-based permission? And let's talk about the differences between identity-based and resource-based policies. They're basically identical, but there's some slight differences. The big difference is where they're applied. An identity-based permission is attached to an AWS identity and access management user, and it indicates what the user is permitted to do. But a resource-based permission is attached to a particular resource, and it indicates what a specific user or group of users is permitted to do with the resource. So this is a great policy, for example, for, let's say, like personnel data, right? You would want to protect that particular resource in a way that is special, maybe than other particular parts of the system. So what are the key takeaways here that we care about? Well, the key takeaway is that you want to encrypt data at rest to make it difficult for attackers to compromise data. This is a layered permission model. You also want to store the data in S3 by, really at private by default and require AWS credentials for access. You don't want to just automatically open things up. And the other key thing to remember is there's identity-based or user-based levels of control, and there's also resource-based levels of control. Okay, let's talk next here about the protection features of S3 here. And some of the things to consider are you can block public ACLs, so you can prevent any new operations to make buckets or objects public by creating an ACL, and the existing policies and ACLs for buckets are not modified. You can also do ignore public ACLs, so you can ignore all public ACLs in buckets. You can also block public policy, so you can reject calls to put a bucket policy in place if the specified bucket policy allows public access. And you can also restrict public buckets, so you can restrict access to a bucket with a public policy to only AWS services and authorized users with a bucket owner's account. So these are also independent, but they can be used in combination. So I think the key takeaway here is that why wouldn't you prevent things from the very beginning so that there isn't an accidental leak of data? And I think this is a very good way to think about things. We also have the concept of versioning. And what's interesting about versioning is that you can think of it as a security feature because you're keeping multiple variants of an object in the same bucket. So you can preserve, retrieve, and restore each of the version. So this means that if there's an accidental deletion or overwrite, you're protected. But instead of removing it permanently, you can just put a delete marker, which becomes the current object version. And if you overwrite an object, you can always restore the previous version. So this is critical for also being able to protect yourself from, let's say, a breach, right? Where maybe a hacker was able to get access to a bucket and they were able to mutate the data or make a subtle change to it. You could always go back in time, looking at the audit logs, and then restoring before this breach actually occurred. So this is, I think, a critical additional factor to consider. Also, there's something called object lock, which is also a great capability in that you can actually have a write once, read many model. This is called worm, and this is a layer of protection where it's important that the data is never mutated. And the feature can provide protection for a fixed amount of time or even indefinitely. So you could use this to meet the regulatory requirements for worm storage. So I think a good example of this would be maybe health data. Why would, if you're collecting some kind of, medical record, why would it be possible to mutate someone's medical record without doing extraordinary things, because the medical record is the medical record. So really critical feature here to consider in security. So the big takeaways here in terms of what we covered are that you want to block public access to make sure that objects never have public access now or even in the future. And that would be really a system-wide consideration. You also want to version things so that you can retrieve and restore every version of the object stored in S3. And you also want to have object lock so that you're preventing people from deleting or overwriting for either a fixed amount of time or even in some cases indefinitely. So the next thing to consider would be protection through encryption. So let's go ahead and talk about that. So why do we care about encryption? Encryption works by using an algorithm with a key that converts plain text data into unreadable data. This would be called ciphertext. But the difference between like old school ciphers and the new ones is that these are actually mathematically unbreakable. So, for example, if you put a "hello world," phrase in a phrase inside, it would be, gibberish, basically. And several different encryption algorithms also work, but they all require a different kind of key. But the key takeaway here is that a strong encryption algorithm would rely on mathematical properties to produce the ciphertext that cannot be decrypted by, let's say, statistical analysis, which older ciphers were easily, breakable because you could look at the frequency of, let's say, a letter in a particular language. So it's really important in this scenario to protect and manage the keys, because the keys are essentially the weak link in terms of security. Now, if we look at comparing the client side and the server side protections here, we can see that you can use client side encryption, CSE, or server side encryption, SSE, to encrypt your data. And there are some differences. So with client side encryption, your application encrypts data locally before you submit it to AWS, and you decrypt the data after receiving it from AWS. With server side, or SSE, the data is encrypted at its destination by the application or the service that receives it. AWS will support both of these. And most of the AWS services that store or manage customer data offer an SSE, which is, again, server-side encryption, or they perform SSE on the data just by default. So let's talk next here about client-side encryption. In terms of client-side encryption, it is a critical component, and it enables you to use it by tapping into services like AWS KMS. Also, in terms of the server-side encryption here, this would be making sure that the data is encrypted as destination by the application or service that receives it. So your source data comes from a system in the data center or an EC2 instance. You would then, let's say, upload the data over an HTTPS connection to any of the AWS services that support the automatic server-side encryption. So let's talk about the different kinds of automatic server-side encryption. So SSE with customer-supported keys, that would be a customer-provided key where you would manage the encryption keys. Another one would be the SSE with Amazon S3 managed keys. So when you use server-side encryption with S3, each object, and Amazon would manage these keys, each object is encrypted with a unique key. And then we also have SSE with AWS KMS keys. So this would be server-side encryption with AWS KMS keys. It would be very similar to the SSE S3, but the additional benefit would be that you also have separate permissions for the use of the KMS key. All right, let's talk about encryption overview next here. In this particular diagram, you would upload a file and store it in an encrypted object in S3. Your Amazon S3 request then would grab the data from AWS KMS to use the ability to encrypt it, and then KMS would provide a plain text data key and encrypt the data by using the customer managed key. And then KMS would then send a copy of the data to S3, and then Amazon would encrypt that object by using the plain text data, storing the object, and then deleting the plain text data key. And so this is all done for you automatically, which is great. So if we look at the decryption overview here, you request to open the object. Amazon S3 notices the object is encrypted. It then sends the encrypted copy of the data key that the object is encrypted with to the AWS KMS system. AWS KMS then would decrypt that data by using the customer managed key, which would never leave the AWS KMS service. Amazon KMS then sends a plain text data key back to S3, and then Amazon S3 decrypts the ciphertext of the data object, which then lets you use that object, and then it would delete that plain text copy of the data key. Let's talk through here about the KMS service, which we've been talking quite a bit about. The KMS is a managed service that provides the ability to create and control the keys that are used to decrypt your data. And the service uses validated security modules at a hardware level, and it's also integrated with the rest of the services. So what would be an example of this? If we look at block storage, this would be a good example and a straightforward way to look at it, where you would say Amazon EBS would obtain an encrypted data key. The service that is running the EC2 instances would then retrieve the encrypted data. A call is then made to the service, the KMS service, and then finally the decrypted data is stored in memory and is used to encrypt and decrypt all the data going to and from the EBS volume. So what are the key takeaways here? The key takeaways are that there are different kinds of client-side and server-side encryption, and there are 3 types of server-side encryption as well. And Amazon KMS is used to control the keys and really act as a high-level service for encryption. Okay, let's talk through here about some other things. Let's talk about protecting data in transit next here. So in terms of protecting data in transit, the key takeaway here is that what you're trying to do is make sure that when you move the data from one location to another, for example, through the internet, nobody's able to intercept that and do something with the data. Some of the things to consider would be accidental information disclosure, data integrity, man-in-the-middle attacks, identity spoofing. So there's some serious things here that can happen if you don't have encryption throughout your connection. So how would you actually do this? Well, the big things to consider would be that you could use the SSL endpoints that would encrypt the web-based traffic. And in order to protect the data in transit, you could do a multi-level approach. So you would use the AWS data centers, and then you would use a VPC, and then also you would use the TLS or transport layer security, and then all TLS connections would secure HTTPS to make API requests. So you've got multiple layers here that are protecting you. Now, in terms of remote connections to servers, a user who would access even Windows terminal can use the Microsoft Remote Desktop Protocol, or RDP. And so RDP would establish a SSL connection, and you would be secure as well because of that end-to-end encryption. Also with SSH, this would be the preferred way to connect to machines, and this is encrypted end-to-end as well. Now, in terms of the AWS Certificate Manager here, this is another one to consider. The Certificate Manager provides a single interface to manage both public and private certificates, meaning that it can be a way to protect and manage the private certificates. So let's talk through what that would look like. So, for example, a scenario would be if you wanted to create encrypted TLS communication, you wanted to do authentication of users, or you wanted to do cryptographic signing. These would all be mechanisms for that. In terms of private considerations here, it would be secured with HSMs, and these HSMs would adhere to the FIPS 142 Level 3 security standards to protect your private CA against key compromises. Key takeaways here are that you want to protect the data in transit, use VPCs, use the ACM service, and also you can do ACM private CA. All right, let's talk about best practices for S3 here. So some of the best practices for S3 include using basically pre-signed URLs. And the advantage of this is that it's only temporary access. So if that was leaked out, you wouldn't need to worry about it. And you can also essentially have a more layered security model using this approach. So what are some of the other considerations here? Use encryption as an additional access control. Use bucket policies. Set the IAM and bucket policies. Also make sure that there's MFA delete. So you'd have to have a separate device that would, be requested if you're going to delete something. Enforce server-side encryption, and then use pre-signed URL. So really this layered security approach is a great approach for S3. Now, what else can we think about doing? Another one would be default encryption on a bucket, S3 object lock, S3 public access settings, uploading data to S3 using SFTP, which is a secure FTP, and also using S3 versioning as well. Okay, what about additional data protection services here? So another data protection service is the Secrets Manager, which makes it easier to manage secrets. And these could be like, let's say, database credentials, passwords, third-party API keys, or even just random text. And you can actually access these via the AWS CLI, API or SDK. So this is really a cool service here that helps you increase security. And in terms of Secret Manager as well, the clients would be able to call RESTful API hosted on API Gateway. You could also do API Gateway runs for Lambda function, and you could actually retrieve those secrets. So this is a really cool service to be aware of. In terms of rotating the secrets, here's a good strategy here. You would have a function that contacts the DB for a new credential. The manager would then store the credential with AWS spending label. The new credentials are tested, and then they're made default with AWS current label. And then in terms of Macie as well, this is another service that's a machine learning service that would discover, classify, and protect sensitive data. So this is really a kind of unsupervised machine learning approach where you look for outliers. You can also classify things like business critical data at a bucket level, and then Macie will continually monitor all those buckets. So pretty slick service. So in summary, what does Macie actually do? Well, it gives you a console here that shows you really like a high-level security overview of what's happening. And then you could look at the findings as well, and it would show you, different things that are happening. So the key takeaways for this would be that, Secrets Manager help protect the access to applications, services, and resources. And then Macie is an ML and pattern matching service that protects sensitive data. So let's go ahead and wrap up this section here and talk about what we covered. So we talked about S3 protection, encrypting data in S3, and then how to differentiate between CSE and SSE, and identify AWS services that help you protect your data. So really that's it in a nutshell. Thanks for hanging in there for this particular session. I'll see you in a week, and we'll cover the next section of AWS Security Certification.